In this video, I'll be discussing thin film interference. It's part of topic 9.3 in the IB Physics Syllabus. Please just take a moment and read the success criteria for this video. It describes what I would like to try and convey. So let's start off by looking at this butterfly. So first of all, if I took the scales off this butterfly, let's say it died of natural causes, and now I'm not being mean, and ground up those scales, there's actually no blue color there at all. It all comes from interference. So what's going to happen is when the lights are shining on it, remember light can interact with material in three ways. It can be absorbed, reflected, or transmitted. So light's going to be hitting the top of the scale and being reflected. Some will be absorbed, some will transmit through, and the same is going to happen on the back end of the scale. So all we're actually seeing is light that's being reflected back to us that has the wavelength associated with the blue color. So what would it look like if I flashed red light on this butterfly? Stop and take a think. I hope you thought that it's going to be black, because right now all I'm getting is blue light. All of the other colors are either absorbed or, as we're going to talk about later, would have had destructive interference. Now, before we can get to that, we need to talk a little bit about what happens when light is reflected, and this is true for any wave. So you can see here I've got a picture taken from the PhET simulation, Waves on a String. The website is there listed below. And you can see that what I have is I have a pulse. And this machine here will create a pulse. In this case, it's created a peak, and it's moving in this direction all the way down to the end. And you can see here it's being held tightly. So stop and think, what's going to happen to that wave when it gets reflected from the end that's being held tight? Now, I hope this is what you thought of. It's actually going to be inverted on the way back. Now, when we're talking about waves, we're going to be talking about it undergoing a phase change of pi, 1/2 of the cycle. So when my peak came on the way down here and I got to the end, we have Newton's third law happening. The wave is trying to pull the beads up, and then with Newton's third law, this is being fixed, so it then puts another force on them back down, and actually then the wave gets inverted. Now what I've done here is I've changed the end to what we call a loose end. So don't ask me why, but the string in that wave is magically being held up there in the air and it's not falling down. But now when I have my wave going to the end, it's not going to be held in the fixed position. You can see here that it's open. So in other words, this end can actually slide up and down as the wave gets reflected. So what do you think will happen this time? It's not going to be inverted this time. We don't have Newton's third law being applied to the grip and then it being back on the wave. So in fact, when it gets reflected, if it came in as a peak, it's going to leave as a peak. So this idea of the kind of reflection and what's happening at the boundary where the reflection occurs is going to be really important when we talk about what happens when light gets reflected when we go from one boundary to another. Now, first of all, so I've got air, then oil, then water. So the thin film is the oil that's nestled in between the air and the water. Now, I've got this drawn as a ray coming in on an angle, but I want you to actually think about it as if it was coming straight down and straight back. The reason being is I only want to talk about reflection, and I don't want to actually think about refraction that could be occurring. As you know by now, any ray coming in along the normal will not be refracted. Okay, so what I have here is I have a ray coming in, and at this junction, some will be reflected, some will be transmitted, and I'm not showing if any is being absorbed. What we have, though, is that the index of refraction of air is 1. I'll tell you that the index of refraction of water is 1.3. And let's assume that the index of this oil, I don't know, let's make it up. Let's say it's 1.5. So what's going to happen here? The light that's coming in at this boundary here is going to bounce from a place where it's optically less dense to a place where it's optically more dense. The wave will be traveling faster here than here. The light will slow down when it travels in something with an index of refraction greater than 1. You may recall one of the ways to calculate the index of refraction, or the refractive index, is to take the speed of light in a vacuum and divide it by the speed of light in the medium. And since the speed of light in the vacuum is the fastest it will go, this value will always have a number greater in the denominator, so that means this value is always greater than 1. Okay, so I can see here then, from these index of refraction, light will be traveling faster and then slower. I also know then that this is less optically dense than this one. And this will be just like our wave hitting that fixed end like we did before. So if it was coming in and it was right here as a peak, after the reflection, I would get a trough. So I will get a phase change. We say it's a phase change of pi. So remember, if it came in as a peak, it comes out as a trough. That's 1/2 through the cycle. 1 full cycle is 2 pi. So from peak to trough, half a cycle, that is a phase change of pi. Now we have something else going on. If you take a look, this ray here that's now going to travel through the oil, when it hits this boundary, now I'm going from something that's more optically dense to less optically dense. So in this case, I will not have a phase change. Now this is one of the key things to think about in this section. It's the one time where I say, oh, I really don't like my data booklet. Normally, I love my data booklet, but in this section, not so much. Yes, there are some equations in the data booklet, but they are only for a very specific set of circumstances. And in HL, we might have varying types. So what you need to do is you need to look at the situation that you have here. You first need to say, do I have a phase change or do I not? And now the next thing we need to think about is, do I want constructive interference or destructive interference? Now remember, if I want this wave here, let's do constructive first. That means if it started off as a peak right here, this ray has now been changed to a trough. That means I need this one to travel far enough so that when it gets back here, it will be a trough as well. That means I need to consider how far of a path difference do I need in order to get them back in phase. And in this case, I have to make up for that one phase change, which means I'm going to have my path difference be lambda over 2. If this ray here travels a distance of lambda over 2, then when it gets back to this surface, then I'm going to have it back in phase with this ray here, and I will get constructive interference. Now let's think about if I want to have destructive interference. Now what's going to happen is my wave is going to have to travel a full wavelength longer than this one. Why? Because this one had a phase change of pi. This one does not. So if I just travel one wavelength down and one wavelength back, it's actually going to be out of phase. Now realize these are just for the first time we could get constructive or destructive interference. If I, for this destructive interference, instead of it having a path difference of pi, I could have had it times any wavelength number, any whole number. It could have been 2 pi, 4 pi, 15 pi, and it would have been back exactly out of phase to get destructive interference. For my constructive path interference, again, my first time would have been with it traveling lambda over 2, but I could have added any number of wavelengths to that. So it could have been 3 lambda over 2, 5 lambda over 2, and I still would have got constructive path difference. Now this is the path difference. If you think about it, that's going to be the distance from here and back again. So if I'm actually asking for the thickness of that oil, it would be 1/2 of the path difference. Now here is where we could change things up. This is only valid right now because I told you we have n equals 1 to n equals 5 to n equals 1.33. But let's say that we have something different in the middle, and now instead of it being 1.55, let's say it's a 1.2. Let's see how that actually is going to change our values. Let's walk ourselves through this again. Now, if I go from n equals 1 to n equals 2, will there be a phase change? The answer? Yes, there will be a phase change because that's going from a less optically dense to a more optically dense. And down here at the second boundary, from n equals 1.2 to n equals 1.33, will there be a phase change? Yes. Again, because it's the relative values that I need to look at, it's going from a less optically dense to a more optically dense. So now if I want them to have constructive interference, it means both of them are going to undergo a phase change. So when it comes to my path difference, if I want them back in phase, what I need then is now I need this to travel one whole wavelength. If I want this to travel and create destructive interference, I'm going to need it to travel half a wavelength. Take a moment and make sure you can agree with those. Again, remember, I could have any multiple of lambda of those, so this could have been n lambda for constructive plus any number of wavelength here for destructive. And this is why I'm saying you want to make sure that you've got this for any kind of situation. First, make sure you know what's happening in terms of index of refractions. Second, determine if there's going to be a phase change or not. Third, figure out the path difference for the second ray in order to create either your constructive or destructive interference as required by the question. And then, last of all, don't forget that path difference is there and back. So if you want the thickness of this film, you will have to divide that by 2. But we're not quite done yet. One last thing to think about is what wavelength are we really using when we talk about the path difference. So if I have a certain wavelength coming in here from air, and then it goes into our soap film, for example in this case, when it's traveled from one medium to the other, we know that it has slowed down because this is more optically dense. If that's the case, remember, our frequency is going to be the same. It's not changed when we have a wave traveling from one medium to another. If the speed decreases, then actually our wavelength will decrease as well. So if you take a look what I have here, I have the first part. Now this does come from our data booklet. N1 over N2 equals V2 over V1. That's part of Snell's law back in topic 4.3. What have I done here? From V2, I've then said that's the same as lambda 2 F2. All I've done there is I've used the wave equation. Now, since the frequency is going to be the same in both medium, I can then simplify this down to lambda 2 is going to be N1 over N2 times lambda 1. Now, in the case of air, we know that the index of refraction of air is 1, so this would actually then look just like lambda 2 equals lambda 1 over N2. But remember, that is only valid if it's going from air to somewhere else. I would recommend that you actually think about this one here so that we have ability to calculate it no matter what our initial medium is. So let's use another example here of soap bubbles. So if I have my soap bubble here and it's held vertically, one of the things for us to realize is it's thinner at the top and fatter at the bottom. Okay, and so when I have this thin film interference happening, I'm going to have a different thickness at the top than I do at the bottom. So because all of our colors from white light have their own wavelength, you can see here that I'm actually going to get different colors. Where I see them is where that particular wavelength is going to have constructive interference. I don't see blue right here, probably because it's destructive interfering, but more importantly, this is where red is going to constructively interfere. We'll always see black at the top of the soap bubble, and that's because it's going to be so thin. At this point, if you remember when I went from air to glass and air, I would have one of the rays had a phase shift and the other one did not. That means I'm always going to get destructive interference wherever the two pieces of glass touch, or in this case when it's very, very thin. Another really common example is something called Newton's rings. Now this was first used by scientists when they were trying to make lenses back in the 1800s before they had precise measurement tools. So if you see here on the top, I've got a plano-convex, one of the two, lens. Plane means flat on one side, curved on the other. And the whole point about this is we want to have an even curve and it's going to be the same all the way around. If not, it's not going to be working very well as a lens. If I take this and I just have a flat piece of glass underneath and I put my lens over top, what's going to happen is I'm going to have light again. I'm going to have reflection from this side, and I'm also going to have it from here. So from the bottom edge of the curved shape and the top edge of the flat shape, those are the two rays that are actually going to interfere together to give me these constructive and destructive interferences that you can see. Now in this case, they're nicely circular concentric rings, and that tells me that my curvature must be pretty consistent and the thickness increases gradually. That's why they're all nicely spaced. Now you can see in this one, first of all, I have light that is colored rather than a single wavelength. That's going to do one thing in terms of I get colored rings because each of the wavelengths are going to occur at different spots. It also is not a very good lens because it doesn't make a nice even circle. Okay, so let's try out a question. Here we have monochromatic light. So remember, light of one wavelength. Yes, chromatic tends to be color, but in physics we prefer to say one wavelength. It's incident on my thin soap, and for some reason it's suspended in air, so I've got air, soap, air. It asks me to label with the letter P where the phase difference of pi is going to occur. So if I'm going to get a phase shift happening, I'm going to go from a low index of refraction to a higher index of refraction, a high speed to a low speed. And that will occur here, at this boundary. Does it occur at the bottom boundary? No, because that would be from a high index of refraction to a low index of refraction. Part B. White light is now being used instead of our monochromatic one. We have a thickness of D of the soap film, and refractive index is given to us as 1.34. Show that for the longest wavelength of light that we could have destructive interference is 6.03 nanometers. And notice it's going to want us to have the light wavelength in air. Okay, so let's stop and think about what we've got here. We know that one boundary is going to have a phase shift and the other does not. And we are looking for destructive interference. So what do I need for path difference if I'm going to get destructive interference in this case? Stop and think. That's right, I want a path difference of lambda. And we want to have the longest wavelength, so I'm going to use lambda and not some multiple of lambda. Okay, so we've got the path difference. That means the thickness is going to be lambda over 2. And in this case, they gave me the value of D. And that will give me a wavelength of 450 nanometers. But we're not done. That's actually going to be the wavelength in my soap film. What I need is the wavelength in the air. And when I put my values in, I'm going to get 603 nanometers. The last part here, why will the soap film appear colored? Well, for 2 marks, you're going to have to describe to me, first of all, that we're going to have white light made up of different wavelengths. And because of the path difference, then I'm going to have a different thickness that will give us a different interference pattern for each wavelength. So if I want constructive interference to see the blue color, I need a thickness so that the wavelength of blue will constructively interfere. And this will be different from red. So take a moment again and read the success criteria. I hope this video has helped you with these.